we're going to start dealing with things that are moving in a circular path. Okay? This does not mean things that are spinning or rotating. It just means things that are moving in a circular path or an orbit. Okay? So in this chapter, we're going to deal with things rotating in this circular path, and we're going to deal with planets in orbit, okay, and how they move in their orbital path. So if we talk about what causes an object to move in a straight line, how do I get an object to move in a straight line? It's not that, it's a lot easier. It's exactly what you think. Okay? We apply a force to it, right? We apply some force. So in order for an object to move in a straight line, there's got to be a net force that's happening in the direction of that motion. Okay, so it could be a push, it could be a pull, whatever it is. It's going to be something that's a net force applied in that direction. Okay, what has to happen for an object to move in a projectile path, right? What's a projectile path look like? Let me see, like with your hand, show me what a projectile looks like. Up and back down, right? A projectile moves in both the vertical and the horizontal direction. So in order for an object to move in a projectile path, what has to happen to it? Yeah, we have to project it, yeah? We've got to have a force at an angle, or two components to our force, a horizontal and a vertical force. Okay, so for an object to move in a projectile path, we've got to have a net force at the angle in the direction of that motion. So we've got to project things up at an angle in order for them to move in both the x and the y directions. Okay? When we look at objects in a circular motion or a circular path, they have similar properties to projectile motions. Okay? They're moving in both that horizontal and vertical direction. So here's a couple things that we're going to study for this chapter. You don't have to necessarily write down these goals. Whoa, sorry. Okay, this is what we're going to look at for basically the majority of this chapter is we're going to connect Newton's laws to circular motion. All right, so when we talk about circular motion, we're talking about uniform. What's it mean for something to be uniform? It's the same. It's identical throughout. So we're looking at uniform circular motion, which means it's moving at a constant speed in that circular path. Okay, moving at a constant speed. In order for something to have velocity, it has to have what two things? Magnitude and direction. Hopefully you could say those without looking at the board. Okay, magnitude and direction must have both of those two things. In uniform circular motion, we say it has constant velocity, okay? But realistically, it has constant speed because the magnitude of our velocity does not change, but their direction does. Okay, so if something's moving in a circular path, the rate or the distance it's covering over time is not changing, but its direction is constantly changing if it's moving in a circular path. Right? Does that make sense? As something moves around a circle, its direction is changing with every single movement, but its speed is not, or the magnitude of that velocity is not changing. If we know that the acceleration of an object is the rate or the change of the velocity, can we expect these circular objects, these objects in circular motion to have an acceleration? Okay? Kind of. Okay, so since our velocity is changing continuously, okay, via its direction, an object is constantly accelerating. Okay, so this is where it gets a little bit tricky. We say acceleration is a change in velocity, and if we know this object's velocity is changing via its direction component, that means the acceleration is constant. It's constantly accelerating. It doesn't necessarily mean that it's getting faster or slower. It means that the direction of that velocity is changing. Okay, which means the direction of the acceleration is changing. Oops. Okay, so that's where it gets a little bit trickier. Motion or things moving in a circle, we're looking at extremely small time intervals. So we're looking at every little motion that object makes as it moves around the circle. And we want to look at that at a really kind of small derivative type time interval. Okay? We are not going to go into derivatives, but we're looking at such a small time interval that we see a kind of an infinitely small change with every single second of time that goes by. Does that make sense? We're looking at extremely small intervals of time. Okay? So, for our point of view, when I say calculate the velocity at this time, I'm basically looking at this one split second in time. Okay, so I want to know at that exact moment what's its velocity. We're not going to look at derivatives. We're just going to look at that one single kind of freeze frame of time. Okay. So let's take a look at this diagram here. If you want to open your book to get a better view of what's happening here, you can open your book to the very beginning of chapter 5, and you might be able to see it a little bit better if you can't see it up here. Okay, at V1, if the object were to be removed from its path, it would travel in that exact direction. So here we see our object moving in a circular path, okay, in this direction. So it's moving in a circle, it looks like this, okay, blah, 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 it's moving in a circle, okay. If for some reason it removed itself from that circular path, it would not continue to travel in a circle. All right, so if we were to remove an object from a circular path, would it keep going in this circular path if I let go? No. What would it do? Yeah, I don't really want to see it hit someone in the face here, okay? But if I were to remove this object from its circular path, it would not just keep just randomly going in a circle, okay? It would move what we call tangent to the path. Okay? So as we see this thing, it would fly off in that straight direction at that instant. Only at that instant in that revolution would it leave in that direction. If it moves farther to the circle, it would leave in this direction. As it moves farther around the circle, it would leave in a little different path. So that's what we call tangent to the curve or tangent to the path. Okay?
Oh, equation.
Okay, so basically we can go through a lot of math that I'm not interested in walking you through, okay? You can follow along if you would really, really like to do that. But when we're looking at the acceleration now of our object, we can use this equation, okay? And this R stands for radial acceleration or centripetal acceleration, okay? You'll hear me call it centripetal acceleration. Your book puts this little R in here for radial acceleration, okay? Centripetal and radial, they mean the same thing. Okay, but here we're in meters per second squared still for acceleration. Velocity is meters per second. What does this R probably stand for? The radius. Okay, and what would our units for radius probably have to be?
I don't even know.
No, you know. Meters per second. Meters per second squared. You probably want it in meters. Okay. So our radius is in meters. So here's our definition of our centripetal acceleration. An object moving in a circle with a radius r with constant speed v has an acceleration whose direction is toward the center of the circle. Okay? Toward the center of the circle. That means the acceleration vector is always pointing toward the center of the circle. So as we spin this, if you would spin this around, okay, where does it kind of feel like your object is being pulled toward? Okay, if you do this, which I don't really want anyone to do this right now, but okay, if you would do this, it feels almost kind of like that object is pulling away from you, but you are pulling it back in with this string. Okay, so that kind of give and take relationship is where we can see this centripetal acceleration coming into play. Okay, centripetal, when I say centripetal acceleration and radial acceleration, the same thing. Centripetal means center seeking. Okay, so that's why we say it's toward the center of the circle. Okay, so as the radius of the circle increases, the slower the acceleration becomes, because as we increase our denominator here, okay, that would decrease our acceleration. Does that make sense? The bigger our circle is, the less often our acceleration is going to change. Okay? So when we look at the path of our centripetal velocity and centripetal acceleration, it would look something like this. Okay? As my object is moving in my circular path, Okay, let's say that we're moving in this direction. Okay, so here's my object. If it were to leave the circle at this point, it would have a velocity that is what? Tangent. Tangent to the curve or tangent to the path. It would look something like that, right? If it would leave the circle at that time, that's approximately tangent to the path, right, or tangent to the curve. Do we see that? The acceleration, however, at that point in time is center seeking. So our acceleration is pointing toward the center of the circle. These two vectors should always be perpendicular to each other. Okay, so if I were to ask you what's the acceleration and what's the velocity at this point on my circular path, you have to know that those two vectors should be drawn perpendicular to each other. Okay, it's going to leave there, but it's accelerating toward that center of the circle. Okay. Period and frequency. Have we heard those terms before? Okay, hopefully, maybe. All right, period and frequency. Frequency is a little f. Looks something like this. Okay, and it's often described in terms of this revolutions per second or revolutions per minute or blah, blah, blah. Okay, RPMs, where do we hear that? In your car, right? And RPM stands for revolutions per minute, RPM, okay? So revolutions per minute, revolutions per second, those are frequencies. And basically what they're telling us is it's a revolution or the amount of revolutions per time, okay? So it's revolutions per second. You can give the units for revolutions per second a couple different ways. You can just say, revolutions per second. You could say RPMs if it was revolutions per minute. Sometimes it's even labeled in hertz, which is revolutions per second. Okay, we won't really get to that just yet, but we can. Okay, a couple different ways that we can measure frequency. But what it is it's how many revolutions are taking place in 1 second. Okay, so it's how many revolutions per 1 second. All right, our period, on the other hand, is the reciprocal of that. It's the time that's required to complete 1 revolution. So it's like seconds per revolution. Okay, these two are reciprocals of each other, and you see the relationship right here. Usually the units for period are just seconds because we know it's per 1 revolution. Okay, so let's just think about big picture here. If I can complete 2 revolutions in 1 second, so think about that. 2 revolutions in 1 second. How long does it take for me to complete 1 revolution? A half of a second. So here, it's the same thing. If I can complete 2 revolutions in 1 second, so if my frequency equals 2 revolutions per 1 second, okay, and it's the reciprocal of that, I'm going to be able to say that my t is equal to 1/2. Okay, 1 second per 2 revolutions. That makes sense? We need to be able to plug these in the reciprocal form. So you need to know one or the other. So you'll see it either as t equals 1/f or f equals 1/t. You can write both of those down. Okay, this equation, the centripetal acceleration equation, those should go on your equation sheet because we're going to use those quite a bit. Okay? So hopefully this equation was familiar to most of you. Okay? Circumference is equal to 2 pi r. Why would we even need to know the circumference of a circle in this chapter? Yeah, we could find out how much distance is covered in 1 revolution, right? If I say I've traveled 1 revolution in 4 seconds, now you can even tell me the distance that it's going to be traveling in that 4 seconds or whatever. Okay? So we say the circumference of our circle is 2 pi r, also known as the distance, right? This would also be our distance of our circular path. And what do we know about velocity at its most basic? Velocity is equal to distance over time, right? So now what we're doing is we're connecting the distance traveled around the circle over the period, right? The time it takes to make 1 revolution. That gives us our velocity. Okay? So this is distance around the circle. This is time it takes for one revolution. So time per one revolution. Okay? Are we seeing that? Distance around the entire circle, time it takes to make one revolution around the entire circle gives us our velocity. And it's traveling at a constant speed around the whole circle, so we know it's not changing at any point during that distance that it's traveling. Okay? How do we feel about that? Good? All right. What do our units need to be for radius here? Meters. And what should the units for period be? Seconds, right? Period is a big T, so think of it as in another way of time. Okay? So it should be in seconds. All right, one revolution's one complete trip around the circle, traveling the circumference. That's what we just talked about, so we're good there. All right, let's try some practice here. Okay, 150-gram ball at the end of a string is revolving in a horizontal circle of radius 0.6 meters. Makes 2 revolutions in a second. What's its centripetal acceleration? Okay, so here's a couple things that we're going to have to work through. First thing we're going to do is find the velocity and then solve for our centripetal acceleration. Okay, so let's start listing what we have here. Does mass go into any of our equations? Nah, so we really don't care. Okay, radius is equal to 0.6. 2 revolutions in 1 second. Does that tell us period or frequency? What is time measured in? What is T measured in? Seconds. So that means frequency is revolutions per second. Right? So this is frequency equals 2. This will be a big stumbling block for a lot of you. You'll just assume that's period or you'll assume it's frequency. So please make sure you pay attention to the units and put them in the right spot. Okay? So we want to find centripetal acceleration, and I gave you that equation right here. So far, the only variable that we have is this. Yeah. Okay, so we're going to plug basically, all we have here is radius. We're solving for the acceleration. We need to find the velocity. And our equation for velocity is 2 pi r over t. This equation needs to go on your equation sheet if you don't have that on there already. Okay. Do we know the period? It's 1/2. So the way we found that is we're going to take t equals 1 over f, which is t equals 1 over 2, which is 1/2. Okay, or 0.5. Okay, so we found our period from our frequency. We're going to plug that in here, and what did we get for our velocity?
7.5.
Yeah. 7.54 meters per second. Okay, now we go and plug that in up here. So we're going to take 7.54 squared over 0.6. Yeah. No. Yeah. That should be right. 94.75 meters per second squared. Okay, good. 94.75 meters per second squared. Questions here? Okay. Something I'll show you really quick is if we can use this equation and we know that velocity is 2 pi r over t, okay, we can basically combine these equations to say 2 pi r squared over t squared times r. Okay, if you want to do that. You do not have to, but you can combine that into one if you don't want to solve for velocity by itself first. Okay, that's up to you. Okay, let's try another one here.
will tell you what the period is. Wait, should we change that radius?
We do. We need to change that radius to meters. And our period is in days.
Oh.
Do we want our period in days?
No.
No. All right, let's do this. All right, so we have our radius here equal to 3.84 times 10 to the 8th meters. Yeah? Okay. Our period is equal to, what do we have that in seconds?
2.36 times 10
Okay. All right, we take 27.3 times 24 times 3,600. Okay. So we have our radius in meters. We've got our period in days. We want to find the acceleration now. So why does it say determine the acceleration of the moon toward the earth? Why do you think it's worded that way? Yeah, exactly. The moon is orbiting in an exact circular path around the earth. And since we know all of our acceleration is center-seeking, right, or centripetal, we know it's going technically toward the earth, even though it's going to stay on that circular path. Okay, so our velocity is 2 pi r over t. That's just velocity that we're solving for right now.
Oh, that's just velocity.
Just velocity.
Oh, I did it. Dang it, I cleared it.
And depending on here where you rounded, your answers are going to be a little different. That's okay. Okay, for velocity, I got about 1022.3. Okay, is that what we got for our velocity? 1022.3, or somewhere in that range. Okay, now to solve for our acceleration, we're going to take that squared. Divided by our radius.
Yes, there is. Right, I didn't clear it, but wait, am I right?
All right, let's try this one. Okay, this time it gives us the velocity and it gives us a radius. You're trying to solve for the period this time. So it doesn't have to do the acceleration equation. You're just looking at that velocity equation. Okay, is this how we started setting it up? Okay, and if we want to solve for our bottom variable, what's our trick here? Switch those two. So we would say t equals 2 pi 0.25 over 4. So we got about 0.39. And what's our units for period? Seconds. Okay, it is seconds. I want you to work on this with your partner. Okay, it's a relationship or a ratio type question. A race car is traveling at constant speed. What happens to the centripetal acceleration if the car, if the speed is doubled? So if I double my speed, what's going to happen to my acceleration? Okay, I want you to work that out with your partner. Try a couple, plug in some numbers if you have to. So if we've got, let's say that our constant speed, our velocity at first is 10. Okay, we'll just say our radius is 5. Okay, if we know acceleration is v squared over r. So if my original was 10, that gives me an acceleration of 20, right? 10 squared over 5 is 20. If I double my velocity, is my radius going to change? No. Oops.
Wait.
20 squared over 5, which is 400 over 5, which is, okay, so it's 4 times larger. The reason it's 4 times larger is because of that square. Okay, it's not just double to double because of that square in there. Okay, so if it was not v squared, if it was just v over r and it doubled, then we would see a double in our acceleration as well.